Hello and welcome. This is section 7.3. Great. So 7.3 is all about substitution reactions. And more specifically, we're going to be talking about one-step substitution reactions. But before we get there, let's give a little history about these things. About 100 years ago, two scientists decided that substitution reactions were something super interesting, and they decided to do a whole range of studies and found that there were two types of reaction or mechanisms that these things could be using. The first is a one-step, what we call concerted type of mechanism that is bimolecular, and we'll get into what that means in just a second. And the second type of mechanism they found was a two-step unimolecular type of reaction mechanism. So let's talk about the bimolecular concerted mechanism first. So in this reaction mechanism, what happens is you have the alkyl halide, and the nucleophile attacks the alpha carbon, which then kicks out the halide atom, which then becomes an halide ion, and negatively charged ion directly thereafter, leaving you with an alkyl nucleophile bond and just the halide anion. Now notice you have two fundamental organic chemistry mechanism steps here that we talked about: nucleophilic attack and loss of a leaving group. The attack and the loss both happen in the same step here. And the reaction profile for this reaction looks something like this, where you have the reactants on the left. Energy is always increasing and the reaction progress is always going to the right. You have the reactants on the left. They have to go through a transition state with an activation energy, and once that energy is met, then they go on to products. This is a one-step reaction. It happens with one transition state, and if you notice, there are two molecules that have to participate in this reaction. The alkyl halide must be attacked physically by the nucleophile. So because of that, the rate equation for this step looks like this, where the rate constant, K, is multiplied by the concentration of alkyl halide and the concentration of the nucleophile. Because both of these have an exponent of 1, this is called a second order reaction. And it's also the reason why we call this a bimolecular step, because there are two molecules reacting in the mechanism's slowest step. There's only one step here, so this step must be the slowest one. The slowest step is also sometimes, it's called that because it has the highest activation energy as well. Okay, and as you just saw, the mechanism of this reaction is here, where you have a one-step attack of the nucleophile on the alpha carbon of the alkyl halide. And one very interesting thing about this reaction is that if you use a chiral starting material, such as this 2-bromo, let's see, what is that? That's S2-bromobutane here. If you react that with sodium methoxide as shown, you can actually have full inversion of stereochemistry to give you the R2-bromobutane as shown, because you always have attack that happens on the other side of the bromide. So whereas before this ethyl group was kind of on the right here, now after attack it gets moved over to the left, which inverts the stereochemistry. In addition, please note that you have sodium bromide as a side product, and that the charges are overall conserved to be neutral in this reaction, because you have 1 plus, 1 minus that needs to be there. So I'll add that in now. 1 minus, there we go. And both sides are neutral. Why does this happen though? Well, there are two reasons why you have stereo inversion. There are two reasons why the attack is always from the backside, and one of those is due to molecular orbital theory, because the nucleophile's HOMO attacks the LUMO of the alkyl halide, and the LUMO of the alkyl halide looks like this, where the electron density on one side of the alpha carbon is different than on the other side. And because they have different polarities, as does the other side of the bromide, this one is likely to be the one with partial positive charge, and this is the side that gets attacked. Probably the easiest way to understand why this happens is by looking at the dipoles of the molecules, the alkyl halides, because there's a partial positive charge on the alpha carbon due to the very large and negative halide, or partially negative halide group that's pulling electron density away. And because you have a strong high electron density on one side and a low electron density on the other, the negatively charged nucleophiles are going to be attracted to this region of the molecule. Now let's look at some substrate effects, because we now know that the reaction happens and how it happens, and we know why it happens the way it does. But what we don't know yet is how to make this reaction go faster, and what properties of the molecules we're reacting might make it go slower. So let's look at the reaction rate for this reaction, where we have some alkyl halide. We'll say specifically what they are below, but we have some alkyl halide attacked by an iodide ion to make an R minus, or sorry, an R bonded to, an R here is any alkyl group. It's bonded to an iodide, and we kick off the bromide anion. So if we just look at alpha group effects, we see that talking about the alpha group here, this alpha carbon, if we react bromomethane with iodide, we see that we have a rate of reaction that we're going to say is 1. This is going to be our standard reaction rate. So now when we compare something to this reaction rate, we'll have an idea of how much slower and how much faster it is, and know what the effect of having substitution at the alpha group, the alpha carbon, is. So if we add in one methyl group to have this one bromoethane, the reaction goes 100 times slower due to the extra steric bulk of having a CH3 group attached to the alpha position. Now remember, we were saying that we needed the backside attack to occur, and that's going to be on this side of the molecule. So any extra steric bulk we put on is going to slow down the reaction. And this is very clear to see as we add steric bulk onto the molecule. Having another CH3 group there makes it 10,000 times slower than the original bromomethane. And if you put on a last one to do this tert-butyl bromide, this 2-methyl, 2-bromo, 2-methyl propane, you can see that there is basically no reaction that occurs, even with crazy temperatures and pressures. So the substrate can really affect the rate of the reaction, or it would be the rate constant in this case. Another way that we can influence this reaction is through beta group effects. So if we have substitution at the beta group, what is that going to do to our reaction rate? So in this case, our standard reaction rate is going to be using ethyl bromide, 1 bromoethane, and our beta groups are here. Okay, so we have one beta group there. That's our standard reaction. If we add another carbon onto this this atom, we find that we don't have much reduction, only 20% slower. So it appears that the beta group already doesn't really do as much as the alpha group substitution, because by putting on an extra methyl group in the alpha position, we had 100 times slower reaction rate. But in the beta group effects, we see that there's only a 20% decrease in the reaction rate. If we add on another alkyl group That's a beta carbon as well. If we add on another alkyl group to this, now the reaction rate really starts to slow down, and that's 25 times slower than our original reaction here. I mean, it's still much, much faster than the analogous reaction from above, but it's still pretty slow compared to the molecule without any beta group substitution. And to finish it off and make the tert butyl group on the end here. So again, this is our beta carbon. If we add on this all three CH3 groups to that beta position, now we have a very substantial slowdown because of the steric bulk of this group here. And that's 10,000 times slower than the original reaction. And my question for you is why? I'm saying steric bulk, but what does that mean when we're talking about real thermodynamics here? Because thermodynamics and kinetics are definitely linked. So let's have a look at the reaction profiles of these things and find out why specifically adding on steric bulk is changing the reaction rates. And it becomes pretty clear if we draw these out, because if we consider, if we consider that the reactants here, iodide plus the methyl bromide, has some activation energy before they reach the products, and then we add steric bulk by just adding one methyl group on there, there's a huge change in activation energy. And this activation energy is directly what affects the rate of the reaction at some temperature. So this is showing us that by adding steric bulk, we're increasing the activation energy of this reaction and slowing it down a lot. So the take-home message for substrate effects on SN2 reactions is that increasing the steric bulk at the alpha and beta positions really increases the activation energy, which slows down the rate of the reaction. Now, before we stop at 7.3, remember, there's another type of substitution reaction we haven't covered yet, and that is the two-step unimolecular substitution reaction, also called the SN1 reaction. And in this reaction, you have some alkyl halide, and instead of nucleophilic attack, what happens is that the halide group leaves. So first, you have loss of a leaving group to generate a carbocation and the halide, the negatively charged halide atom, and then you have nucleophilic attack on the carbocation to make the nucleophile alkyl bond, and you still have the halide ion around. Please notice the first reaction is in equilibrium because you could have loss of a leaving group and then this atom, this ion, just reattack it directly to go back. So you have some equilibrium between these two molecules, but then once it's attacked by the nucleophile, we're considering that the reaction is finished and this is an irreversible step. And the reaction profile for this looks a little different than for the SN2 reaction because you start with one molecule, and that one molecule has an activation energy to get over this transition state to the intermediate state, which is the carbocation plus the negatively charged anion. And then there's a second activation energy that is needed to have the nucleophile attack the carbocation and form the products. And because the first activation energy is much larger than the second activation energy, the first step goes slower. And since it's the slowest step in the reaction, we consider that to be the most important step to think about the kinetics of this reaction, or the overall rate law, as we call it. So because of that, the rate law for this reaction looks like this, where you have the rate is equal to the rate constant only times the concentration of alkyl halide, because this is the slowest step. So because this goes much slower, the reaction can proceed pretty quickly after this step. To just recount on this two-step unimolecular substitution reaction, or SN1, we have two steps with one molecule doing the work in each step. You have an intermediate and two transition states, and the rate law that is unimolecular and first order because you only have one power here with the alkyl halide. So that is section 7.3.